that as well. Let's check. Still not enough students, but it's 8:55, so we start with the content. So exercise, get ready with your exercise, and this is the target of the afternoon session. Right, do we need that? Yeah, let's keep it open. And where are my slides? Here are my slides, and we move to that. So last time we met, we discussed the aspects of the protocol, that it is useful to have protocols. If we didn't have protocols, then of course our systems, our internet as we know it wouldn't work, at least not the way we know it now, where every system is interacting, where we can open up web pages freely. Therefore, protocols are necessary. And if you think back to the design dimensions of distributed systems, this openness was one of the primary design goals. And of course, the specification of a protocol that enables other computers to interact with each other is, of course, a significant part of this openness design goal. And what we now do is targeting another design goal of these distributed information systems. They also target this openness because they also are specified based on protocols, based on rules, based on formats that allow the usage of the so-called middleware. And they target the different other design aspect of distributed information systems, namely this transparency, where it was a task to hide complexity. Of course, the primary goal is to hide complexity from the users, but there's also a transparency for us programmers, where specific complexity, specific tasks are done in the background, just as it is done by TCP in the background on the socket aspect, because we don't see how the TCP socket itself chunks the stream of data we want to communicate. It is hidden from us, but in the background, of course, the socket itself adds some header information, adds some trailing information, and then communicates it over the network. And this chunking and additionally added metadata is something we know about because we can look it up in books, or if we listen on the network, even on a deeper layer, we can actually see that. But from the layer we were working with, the sockets, it was transparently done in the background. And of course, this transparently done in the background can be also conducted at a higher level. And this is exactly what we will be using, or where we will turn our focus to now, because next step is taking a look at the so-called middleware, and later on use different middleware technologies, different communication middleware technologies to achieve this communication goal in a more easier way. And therefore, from a programming perspective, of course, this is, if you need to implement that, it's of course a nice thing. Nevertheless, in the background, always sockets are used, and they shift byte streams around. And but from the perspective when we are using middleware, we don't see that anymore. It's hidden in the background. But nevertheless, it's done just the way we did it in our exercise. So let's take a look at the middleware. So what's the motivation to integrate a middleware? First of all, every modern internet-based system is, of course, a distributed system because it's in the internet and the browser is locally, and we communicate with a distant server. And of course, all this communication is done via UDP or TCP sockets, and therefore everything we've already done and the amount of work we put in there wasn't in vain. Of course, we know from its specification that every distributed system has multiple components, otherwise it wouldn't be distributed. That can be two, client and server, but in reality, of course, there are multiple other things involved, different servers, different databases, different locations, and everything is working as a homogeneous system. And of course, as we split up this application into different components that are running on different computers, of course, this makes communication between these components extremely valuable because they need to communicate. It's not like in your program where you just say, okay, use this address at this point in the shared memory, and then you can just continue there. In a distributed system, you need to announce, okay, now I want this to be executed, and it is executed on a different computer. And this, of course, makes the necessity of communication even larger, even bigger. And there was something I wanted to say while I was looking for words. Now I dropped it, of course. Damn it. Let's think. Perhaps I stumble upon it again some other time. And this communication, of course, is not only I want to give you data, but I want to use your services. So the servers and the clients, and depending on which focus or in which situation you are, even a server can be a client, because a server can use this different other servers to solve a specific task. And these tasks are typically not store this or give me data like that, but also some calculate me this, transform me that. And typically you want to use these servers that are far away from you or even close by using them similar to what you do when you execute something locally. So the idea is, and this is again this transparency, you want to, your code, your system to look like as if it is working with a fully locally. But in reality, some parts of your application are done in a distributed environment. And therefore, you need to find a mechanism to, for instance, call a method from a specific object. And in reality, this object isn't residing on your computer. It's residing on a server at a different continent. And inside your system and inside your program, you want to have it look like as if everything was locally. And of course, this means that the complexity of these protocols that need to be executed in the background are far higher than those we implement in our exercise. And as always, there are some groups to try to optimize the solution of the exercise by just saying, okay, let's not communicate the name of the method. Let's just use an index. And this is done every year. And of course, you have to think about that. This, of course, works for our exercise. No problem at all. We just have 3 methods. So why not use, if I send it 1, execute method 1. If I send 2, execute method 2, and so on. But if you think about that from and look at it at a greater perspective, then of course you know, okay, what if I have an unlimited amount of methods, because I can choose as a programmer, choose how a method is named. I choose the signature. And then suddenly this index mechanism isn't working anymore. So you need to tell the system, I want to execute this method. And this is done all over the place because you want to store this JSON fragment inside a database. So you need to tell the database server, I want to store something. I want to look up. I want to change. I want to update and stuff like that. And therefore, this indexing is, of course, something that works on a small scale without any problem. But if you want to be more flexible and go bigger, this, of course, is a dead end. And therefore, I typically say, no, you're not allowed to do something like that. And then I'm telling you this, I remembered what I wanted to tell you the moment before. If you think about these, the systems of today, putting services or putting processing power into the cloud using microservices. This is, again, one of these hypes, building systems based on microsystems. So where you have tiny functionality of the overall system being executed in its own process. And if you think about that, it must be clear to you that then using microservices, again, makes your whole application a distributed system, where when you have it all in one process, of course, you execute methods and you can do it in a shared memory. But if you have something like a microservice architecture, then of course these processes, these functionalities are ripped apart, and then these processes need to communicate with each other and exchange their wishes. And of course, this again makes communication necessary. And of course, you need to define how this communication should take place. And if you choose to, for instance, use REST web services, which we will be playing around with later on, you need to be aware that, of course, this means typically communicating via HTTP, which is not optimized at all. And of course, communicating data that is structured to be human readable, which of course is also not optimized in any way. And therefore, this communication is, of course, some sort of bottleneck. But you will find that out once you play around with the cloud services later on. And of course, there are other solutions to this problem, not doing inefficient communication, but using different other communication approaches. But this brings us back to the middleware, because you see, or I hope you see, based on the examples I presented to you, that you open up a can of lots of problems. If this communication needs to be open and you don't know exactly how the methods are named, what parameters to provide, and stuff like that. So the problem is similar to that problem we have in our exercise. You want to execute a specific method on the server side. And all this, what we were working with, specifying the command, checking if the command was right, what happens if the command is not correct, what happens if an error occurs, all this is necessary in millions of places in our systems today. And so everyone is facing the same problem over and over and over again. And of course, reinventing the wheel every time you build a new system is completely inefficient. So of course, scientists already had that problem decades ago. And they realized, okay, not again this problem. And they came up with a solution saying, okay, all this, what is necessary to establish exactly this communication mechanism, why not hide that behind a layer of technology and make it easier to be used. In the background, it can be complex, just as we did in exercise 1, but on top of that, it's just calling methods or seemingly calling methods. And this is what middleware is used for. So it's basically an additional software layer which uses standardized interfaces and protocols, and which takes care, which manages additional inherent tasks in a distributed system. So defining what method to be called, defining how the parameters are, which parameters are necessary, which parameters to use, which values to use, what the return values, what happens if an error occurs, what happens if some data isn't yet fully communicated. All this stuff which makes our life at the level of the sockets hard. And this layer just takes care of it. It hides it from us. And this, of course, makes our life way easier. So all this aspect, transmission security, error handling, and so on. And this is what middleware is about. So it provides solutions to reoccurring tasks in a distributed system. And if you think about that, this is also something that typically is the goal of software patterns, to just help us. Of course, there is not the one middleware. We're on this planet and we have hundreds of solutions for different problems, and sometimes we have hundreds of solutions for the same problem, and sometimes we have the same solution with different names just because we need a different name, because it's the other name is 2 or so decades old, so it's not fancy, and therefore we needed something new, fancy, and give it a new name and sell it as something fancy new. And those of you, and you will experience that later on, you will realize, we've done that again already in the early 2000s or 2020s, and now 2030 or 40, we do it again, but we just name it and give it a different name. Nevertheless, when we take a look at the middleware, that does support us with nerving tasks which need to be done if we are managing a distributed system. Of course, there are middleware technologies that only manage the lower parts. Then are middleware technologies which support us a little bit more, and there are other middleware technologies that even support us a little bit more. And so there are different middleware technologies which aim different, which are differently powerful. And of course, we start again with the least powerful middleware, which just takes place regarding the communication. So middleware technologies that help us establish this communication calling methods of a server that is not running on our machine, that make this aspect easier, and way easier than we've already done it. Later on, we will see there's something like message-oriented middleware, which is quite old technology, nevertheless surprisingly modern at the same time. And of course, application-oriented middleware, where there is even more support for specific aspects that need to be handled and taken care of. Right. So, of course, if we support some kind of middleware, as I said, it looks like as if we are calling methods and telling the system to do something locally. But of course, this doing it locally is just our imagination. In the background, a specific protocol needs to be executed, which typically uses TCP and UDP in the background. And the thing is that when we use the middleware itself, different technologies are available, we typically don't see that anymore. but you need to be aware in the background, of course, there is a protocol defined that just does exactly what we did in the first exercise, specify which method to call and which parameters to provide, and take care of the results. So when we take a look later on the ISO-OSI layered model, we see that there is an additional protocol integrated, but from our usage perspective, from our programming perspective, the transparency design goal kicks in and hides that from us. And we don't see that anymore. But every middleware technology, of course, has a specific protocol that executes in the background. It's not magic that happens. If you call a method, then suddenly magic, woohoo, on the other side of the planet, a server executes this method. Of course, communication is necessary, but we don't see that anymore. And of course, middleware is split up into different layers itself, depending on the complexity of the middleware technology we are using. And of course, every middleware layer uses, again, its own protocols, because as you know, if the complexity, if the amount of, if the problem size is too big, we typically use, our first approach is chunk it, cut it into pieces, structure it, and this, of course, is happening all over the place. And this brings us, and we just use that. But be aware, in the background, they do the same stuff we did in exercise 1. Way more sophisticated, way more sophisticated, but nevertheless similar. Yeah, right. So as we were playing in our first exercise somewhere around here, the next exercise is playing around with the systems somewhere up here. So we will use a middleware which defines some kind of middleware protocol. But of course, this middleware protocol uses the transport layer of the network, and therefore UDP, TCP are involved again, and some bytes are shifted from the client to the server and from the server to the client. But we don't see that anymore. If we want, of course, we can take a look at it, but typically we are quite happy with knowing that someone else takes care of the stuff. And therefore we ignore that typically. Okay, so we first take a look at the communication part of the the lowest level of middleware that we can get our hands on, and this is typically grouped as the communication-oriented middleware. And in the communication-oriented middleware, we have different dials to establish this communication. And there are the so-called remote procedure calls, because this was in the earlier days of computer science. We used procedural programming, and then object-oriented programming came up, and so this was already in place as at the point where we didn't have object-oriented programming languages out in the wild on a broad scale. Of course, some minor things were already object-oriented, but we all learned Pascal and modular, and they were more like procedural programming, and therefore this mechanism was called remote procedure calls. And as the name already states, we want to call a procedure that is remote, that is not running on our system. So the remote procedure calls, I want to execute a method of an object that is not running on my computer or not running in my process. And this on a procedural programming, functional programming perspective. And of course, at some point, object orientation was the thing that needs to be conducted when you program a system. And of course, we cannot stick to remote procedure call because we are not having procedures. So we have to come up with a different name. And the different name was remote method invocation, because objects have methods. And therefore, it's not called remote procedure calls anymore. It's called remote method invocation. Nevertheless, the same concept. I want to call a method of an object that is on a different computer in a different process. So based on this new naming convention and the object-oriented approaches, the different manufacturers came up with specific namings of this remote method invocation idea in their programming languages, environments. And for instance, Microsoft .NET Remoting, and in the Java world, it was called RMI. Be aware, RMI is also the acronym for remote method invocation, and therefore people tend to think that RMI is a strict Java-based technology, which of course is completely stupid. It's just the same name. Java didn't invent remote method invocation. They just choose to use the same name in their programming language. The concept is I want to call a method on a different computer. And of course, the problem that arises based on that is, how do I know which method to call? Which methods are available? I'm a client. I know that I want to do something on a server, but how do I know which methods are available? How do they look like? What's the signature of the method? How do I call them? How can I reach the server? How should I provide my parameters? How can I interpret the results? What happens if during the communication something goes south? All this stuff needs to be taken care of. And the good thing is we don't do that. We just use the middleware, and in the background, the middleware does all that for us, the communication middleware. So we are on the winning side, at least if there is no big error included like this log4j thingy. We are on the safe side. If something like this mega bug is integrated so deep in the system, then of course everyone is in a big problem. Nevertheless, so we have remote procedure calls, we have remote method invocations. We want to call a method of something that is not in our memory space and want to make it look like as if it was. That's these two approaches. Something different is the message-oriented communication. So we want to send a message. Again, well, let's slightly turn the thing around. So this is more like a connected version, and the message-oriented is more like a disconnected version. So we just want to announce what we want to do, and it's more asynchronous integrated. So there is something that is less stream-based as these two, and it's called message-oriented communication. And in the textbooks, there's also some specific versions reserved for streaming, but those are not of our concern in this lecture. So as I said, we will concentrate on this communication-oriented middleware first of all, because it's the one that is typically used by the systems we want to use, or which are the foundation of the fancy libraries, fancy systems we want to use to establish to establish this. I want to call something that is not on my computer. And of course, this communication-oriented middleware is something that gets integrated into the distributed system. So it's basically the idea of everything. The tasks is it provides a specific interface to the communication infrastructure. Namely, it gives us the power to call these methods, procedures, functions as if the system was locally available. And in the background, it automatically transforms our wish into, and of course, the data of our wish into something that can be transported over the network and executed on a distant remote server. And of course, the error handling as well. And that's basically the idea. So our application uses the distributed oriented middleware, which is sitting on top of the distributed system of some kind. And communication-oriented middleware, of course, uses this typical TCP communication on most of the times and does whatever we already did. So what is necessary? Of course, we need this middleware protocol I was already talking about. And depending on which system you are using, typically these systems, so if you're using .NET remoting, they use a different protocol than if you're using Java RMI. They are not typically not interoperable. So this also needs to be taken into account. You need to know if you're using a middleware technology, how open are they? Open is always, yeah, how to express that? It's depends how open you really are. Are you open for everyone, or are you open for people who are part of your party? So, and of course, this is always the same. And so the middleware protocols that are used depend on the system you are on the middleware technology you are using. Java RMI only works and provides its own communication protocol, its middleware protocol, and only works with Java RMI and not with .NET remoting of Microsoft, for instance. Yeah, this of course it gives us the power to communicate between the layers of the different computers. And another thing that is quite nice is where we now had to specify, okay, I want to talk to a computer that uses this IP address or has this IP address, and I want to talk to the service that is hidden behind this port number. Everything is hidden from us. There typically is some kind of broker involved. We just ask the broker, I want to contact this service. So we are not talking about servers anymore. I want to use this service. And the broker tells us, okay, no problem, use this. And in whatever the broker provides us with, there is the knowledge hidden how to reach the server and at which port it is waiting and what language it is speaking, so the protocol used, and then everything is done automatically, even the threading and process management. And something that is also interesting if we play around with distributed systems and middleware technology, a uniform data format. But this is something we take a look at later in more depth later on. So what do we want? The general goal, as I mentioned multiple times, is I want to call a method, a service of another component of the distributed system and is residing on a different machine. Give me some data matching my input I provide you with. And of course, I want to do this in the most simple way. Best would be if I don't even realize that I'm calling something that is residing on a different computer. So the idea is to do it in the most convenient way possible. And of course, we're looking at this communication-oriented middleware from a programmer's perspective. So we build a system, and we don't want to be bothered with all this complexity of the sockets and data management and what is available and how do I need to do this. We don't want to know that. We just want it done. So we want it to be as simple as possible. We would like to have it look like as if we are talking to a local object. So there are some challenges involved. We need to say what we want and transfer the parameters and receive the results, of course. We want, in order to have this done, we need some constructs that do exactly what we want. And of course, these constructs typically need to reside on our computer because they need to establish the communication socket to the server and tell the server what we want. And we need to call this method at some point in time. So this, whatever thing is residing on our computer, needs to somehow behave as if it was offering some specific methods. And in order to achieve that, of course, this in the background again, there needs to be some kind of data transformation. Because we already know when we have a Mac-based system using whatever Swift, and it needs to communicate with a Microsoft system that does something in C++. Then, of course, they do have different sizes for their, or typically they have, would be nice if they haven't, but we are living in this world where everyone wants to do whatever he or she wants to do. And of course, this has been all the time, not only in pandemic times. And therefore, we have a heterogeneous environment. We don't have something that suits all. We have something that suits me best. And therefore, this, of course, brings in some problems. They need to be which need to be solved. So what if an integer has 2 bytes here and 4 bytes there? How do I solve this problem? So the data has to be transformed in some way. And of course, we have different programming languages using Swift. On the other side, we have C++. And of course, they also have, again, different representation forms for different programming for different data types, and of course how to state something. And yeah, at this point in your development, you should know that by now that if you're using different systems, they typically do stuff different ways. And of course, you need to make sure if the Mac Swift client calls a method, then the C++ server in the background realizes, oh, this is what the system wants. And this needs to be solved for heterogeneous hardware and heterogeneous programming languages alike. So there are, of course, different middleware technologies coping with this problem. Some that are specialized on heterogeneous hardware alone, some are specialized lying on top of different programming languages. So they have different abstraction levels to cope with this problem. So sometimes we use a specific middleware installation, and sometimes we have middleware specific data formats, or even better, something that isn't restricted to one platform at all, which is wide open, which is really open. And this is, of course, something that is really nice. So what kind of middleware specific data formats could be of interest? Let's see. Perhaps we make a short break now, because then we can talk about that after the break. So we do that. So before we talk about this middleware specific data format, we make a short break, 5 minutes to 9:40, and then we take a look at this specific aspects of what is happening in the background and what would be useful and what is necessary. Okay, so 5-minute break, and after that we will continue. Right, back again. Let's get, oops, not too far. So before the break, we were talking about what is necessary or what is done in the background to cope with this problem, how to tell or how to define what we want and what needs to be transported over the network. And one thing was that we have different middleware technologies that are used on the different platforms, and typically this middleware technology is defining a proprietary mechanism which cannot be used by other middleware technologies. This is just the way it is. And therefore, the data format that is used inside this specific middleware technology is the necessary common data format. So it defines how the methods are specified. So do I really use the full name, or do I have a byte-coded version of the name, or whatever? And due to this common data format that is used inside the middleware technologies, of course, the client and the server part are able to interpret what they want from each other and what needs to be transmitted. And typically, one example that is printed down in textbooks is the Common Object Request Broker architecture, CORBA. This is something that was envisioned, was it in the 90s? Not sure, but this was some hype. So everyone was, wow, cool, CORBA, because it was something that was run or was designed to run on different hardware systems, on different computers. So this was envisioned as the architecture of our network was even more heterogeneous, and there was some space for development yet. And so scientists thought, let's have something that can be used on different computers, and to cope with the problem that everyone is doing what they want, let's build something on top of that can be used with all of them. And they came up with this CORBA architecture, which was from a design perspective really nice, because the idea being able to use a Mac to communicate with the Sun SPARC station, of course, was sexy at that time. And therefore it was designed, or this was the purpose it was designed for. And nevertheless, it really didn't get off the ground so well. So that's the reason why CORBA is something that some of you may have heard of, but some of you may have, okay, what the hell is CORBA? Is it misspelled and snake-like? But they had quite a lot of nice ideas, and of course it is still working. There are some systems that still are able to use CORBA, but it's not really something that went out broad. Sometimes it's if the industry doesn't want to, and if the people don't zwingen, don't tell the companies what to use, then even a good idea doesn't get off the ground. And sometimes bad ideas go off the ground and they are used all over the place. So in CORBA, for instance, there was this common data representation which was used to convert what we want into a byte array and then reinterpret this byte array. Another example is, of course, the programming language Java. If we have Java on the client side and Java on the server side, we can make our life easy by just serializing an object, converting it into byte stream, sending it over the network. And if on the other side the communication partner uses the same class with the same version ID, then we can just unpack this byte array, convert it into the same object again, similar same object again, and do whatever we want. So the language itself provides this mechanism. And I try to state that in this slide. So the red rectangle specifies what we want. We have a student, and what we do is we serialize the student into a byte array, and then we can communicate this byte array over a network. And on the other side, we can deserialize the byte array, and and the same student pops out again. So this is quite easy. We can just serialize the object, make a byte array out of it, and then use this byte array to be shifted around different computers. And the other rectangles just show how it could be done, and if you are interested. So that's one way. So the middleware technology we use, and .NET Remoting has, of course, something similar. The middleware technology we use specifies a way to communicate data in a form that is valid inside the middleware architecture. Java, Java, Corba, Corba, .NET, .NET, and they exchange data. And of course, why should we be restricted to Java, Java, Corba, Corba, .NET, .NET? Wouldn't it be way better if we had something that was specify something, and I don't care what technology is used at the other side, they also understand what I want from them. So that's the idea of the external data formats. We specify something that is independent of the middleware structure, of the middleware system we are using. And at this point in time, at my point, and when I was in your age and at your stage, XML was just getting off the ground, and it really was something for quite a while. And then XML, Extendable Markup Language, was somewhat, I'm missing the English word, somewhat abgelöst, taken over by JSON, because in our current world, the internet and the browsers and you doing stuff in browsers, of course, this is one of the key aspects we want to do. And there JSON is, of course, quite nice because we can quite easily transform these JavaScript object notation to real objects and data and stuff like that. So these two are quite often used as this external data format to even cross these middleware technology boundaries that are available. So I cannot, as I said, cannot use .NET Remote with Java RMI. But what I can do is I can specify something in XML, give it .NET Remoting, and it can, with enough processing and stuff, understand what is inside this container. And the same goes for the Java side. So they can use that as a means to communicate. And these data exchange formats, based on their different complexity, JSON is less complex than XML. But JSON is not as blown up as XML. So XML has quite a huge overhead, which is the reason why JSON is currently favored, because it has less overhead. Nevertheless, XML has some features that JSON doesn't offer. And of course, you need to decide, okay, do I need these features or are they just overkill? And in my situation, I can go with the less featured version, but faster version. And that's currently the religious war, why XML should not be used and JSON should be favored and stuff like that. And what we will later see is that when we play around with the so-called web services, which are again some kind of middleware technology to being able to execute something on a remote computer, they are quite extensively using XML and JSON to express whatever they want. at least at some parts of their existence. So what we really want to do when we have an external data format, we want to have our student, which we already had in the coding example the way before. And what we do is we convert the student into something that we can read. And that's the nice thing about this point in time at the data exchange formats, that they are still human readable. And of course, this is, if we look at it from a optimization perspective, not a good thing. So it would be better to just have a byte coded data, which would be reduce the amount of data size enormously. But of course, then we would have problems looking at it because we can't read that stuff really. We're not that crazy. So one of the big things inside each of these middleware technologies is always we have something we want to call a method. We call a method. And now this call of a method needs to be transformed into what goes over the communication layer. So we need to transform it into a byte stream. And this transforming what we want into an array of bytes, which we can then communicate over the network, this has a specific name. So the marshalling is taking what we want and converting it into a byte stream. And unmarshalling on the other side is the other way around. We receive a byte stream and then need to unpack the byte stream in order to find out what needs to be done. And this, of course, goes from sending data from the client to the server. And of course, at some point, the server wants to send the result if there is a result expected. And then the server also marshals whatever the result is. An exception occurred, everything is fine, here's your data, and sends it back to the client, which then, of course, is also must unmarshal it. And of course, also in our exercise 1, we had this problem, marshalling the name of the method and the parameters into a byte array, sending it to the server, unmarshalling everything, interpreting what needs to be done, calculating the result, putting the result into a byte container, sending it over the network, unpacking it again on the client side, interpreting it, building the env data class around it and stuff like that. So we already did that, marshalling and unmarshalling. And of course, also in the technologies we will be using from now on, also this marshalling and unmarshalling takes place. But we don't do it anymore. It's done automatically in the background. And then that, of course, is the nice thing. So marshalling is bringing the data, what we want, into the transmission format, and unmarshalling is receiving a transmission format and retransforming it into something that the target machine can realize. So the next question, of course, is who's responsible for that? Who does all that? Who spares us all these problems? And of course, this is done by different components in the target systems. And inside the literature, these house elves, nice little things that help us, also received some names. As it wasn't Harry Potter time at that point in time when this first was envisioned, they of course had different names for that. So in the world of middleware, these components that are responsible converting our wishes into byte arrays and back again are called stubs and skeletons. So stubs and skeletons, if you stumble upon a stub and a skeleton name aspect, then you need to realize, okay, these are parts of the middleware technology structure. that are responsible for marshalling and unmarshalling in a remote procedure call or remote method invocation or in a message-oriented world, doing what needs to be done to transform the data into a communicatable form. And this is basically what is the reason, or what is done. So going back to what we really wanted to do, we want to call something remote and have it look like it was locally. So what we talked about now was how to transfer the parameters and the results. Either we have a platform-dependent middleware system, so Java, Corba, .NET remoting. Then we use the aspects of the language of the middleware technology itself, or we have something that is platform independent or middleware technology independent, like a very specific XML specification or some kind of JSON object that we can communicate. So this has already been, this is what we talked about the minutes before. And so the next step is, how do we get the object that manages the distant remote calls? Because at some point, this knowledge, where is our communication partner and what are the methods I really can call, needs to be defined. And of course, we need to do the call itself. So that brings us to the problem. So what distinguishes a local call from a remote call? So typically in a local call, the procedures methods are executed in the same process. Of course, we call toString, system out, print line, cout, and of course they are executed in our program. On a remote call, this is all, of course, done at a different process that is running on a different computer, and of course that is executed concurrently to the perspective of the local call, of the local caller. The good thing about the local call is they use the same address space, and of course in a remote call they cannot share that because they may reside on different continents. They have the same hardware and software environment because they are running at the same computer and the same process. And of course, in the remote call, this can be completely different. We have a Swift call on a iOS smartphone, and it is triggering a C++ system that is running in some cloud environment of Amazon. And of course, they are completely different. When the local call is calling the method, of course, if in a normal situation, nothing bad can happen. Calls the method executes or returns, everything is fine. So they have the same lifetime. If the local call gets killed, then of course the program ends. In a remote system, of course, these life cycles, of course, are different because you don't know what happens to the cloud service that you are using. Of course, these cloud service providers state that the system will be up 24/7 and everything is fine, but you can never be that sure. These calls are typically, local calls are typically error-free. You just call it, and if the compiler stated you did it in the right manner, typically the call of the method produces no error. Nevertheless, on the remote call, you need to be sure that the system is running and that the network is doing what it should be doing. In today's world, this, of course, is at this point in time no problem. But of course, depending on the distance and where you put your computer, you cannot be sure that this really is as error-free as you anticipate. If you build up high redundancy system, of course, you can be, but think about what happens if you want to support some kind of build a system that supports scientists that are working in remote areas where we don't have any cell towers and no nice internet connection. Of course, we are building up satellite-based internet connections and stuff like that, but there might still be some white spots on the planet. And of course, this brings in additional problems, but only for people who have to tackle the problem or build systems like that. Only applications errors need to be considered. So when you do something locally, you typically just have to make sure that your program runs as it is expected from it. And of course, in a remote call, you sometimes cannot, you have not everything under control. If Amazon decides, okay, we need to shut down the cloud for on Sunday night because we have to make that important update, this could happen. Of course, it will not, because they will try to switch it. There are different other strategies to cope with that problem, which are not part of this lecture. So there's some huge difference between local calls of a method and distant calls of a method, because communication is involved and distance is involved. And we talked about that problems when we talked about distributed systems in general. So let's return to the different technologies that are available. I already told you that when we take a look at the communication-oriented middleware, we have different characterization mechanisms. So due to the linearity of time, it's all started with a procedural, functional approach to this. I want to call a method on a distant computer. So that's one way to take a look at it. And then object-oriented popped up. And of course, it was the next big, huge thing. And we are still using object-oriented programming styles. So this is the other way around. Nevertheless, the idea is the same. And a different communication style, doing it synchronous. So I call a method and wait until the answer returns. It's just like a local call, versus an asynchronous call. So I call something and then do whatever I want to do and wait. At some point some answer returns, and then I manage that answer. So these are the different perspectives that are used inside the literature to look at the different remote models. And this, of course, can be these dimensions can be used to specify the different versions we were talking about. So remote procedure calls, of course, are, as the name already states, procedural, functional, and are synchronous. So I call the method as if it was locally, and I wait for the result. And as it is done, as communication is taking place in the background, of course, I'm blocking there until the result returns. Same goes for the remote method invocation approach, which is object-oriented because we're using methods now, and nevertheless, it's also synchronous. And we have the third opponent or participant, the message-oriented approach, which doesn't care which aspect is used and which is strictly asynchronous. So I send the message what I want to do, and the system is always, yeah, let's do something else during the calculation of the result. So this brings us to, again, these core concept of the remote calls. As we already said, the stub and skeletons are the real important thingies inside our system, because they make sure that the call we initiate on the client side pops up at the server side in the right manner. And this, of course, can only be done based on, again, openness. So we need standardized interface definition languages, which need to be used on that behalf. And typically, these stubs and skeletons are automatically generated. That's the nice thing. We don't need to do or build them when we want to use them. Typically, we just need this specified language which state how they should look like. And then these middleware technologies provide some kind of magic thingies that use this specification and then rebuild them on the client side. On the server side, they are typically already constructed. So once one stub is constructed on the or resides on the client side, so stub is used for the client side, and there is the communication partner. It is also stub, or also sometimes called stub on the server side, but sometimes it's also called skeleton. So sometimes it's stub communicates with stub, and sometimes it's stub communicating with skeleton. And if you stumble upon stub and skeleton, skeleton typically is on the server side. And they are responsible and typo for marshalling and unmarshalling the requests. And they assure this access and location transparency. So you don't know if you call a method of this stub that is inside the client side where this call is going to. So you don't see which IP address and port address is used to initiate the socket communication. It's completely blinded from you, transparently hidden from you. And this is a good thing because, as you saw in exercise 1, this can get quite complicated. So taking a look at that from a more structural perspective, so what is really done? So we have our client machine, which wants to call a method on the server machine. So the client wants to call the add method. And of course, the add method needs to have some parameters. So this is a very simple example, but nevertheless, we always use simple examples. And of course, the result needs to go into some kind of variable. And in our program, it looks like a local call. What really happens is that on the client process, in the client stub, this I want to call the add method, and these values need to be added. Is marshaled into the transport protocol. First of all, it's translated into how should this call be communicated, so into the language of the middleware. And then it's converted into a byte stream that is sent over the network. And on the skeleton side, on the stub of at the server side, it is unpacked again. The byte array is packed into the language of the middleware technology. Taking a look at, okay, and then really a method that is matching this thing is executed. The result is calculated, and then the result goes back all the way to the client and pops out here. And this is what is done inside these middleware technologies. And this is exactly what we did in the first exercise. So we called a method here, and it was transformed here, and the result was communicated back. And of course, communicating 1 for add and 2 for delete and 3 for update might have worked in our exercise, but in real life, where the server process can use any method specification it wants, this of course makes no sense anymore, because it might change, and then what happens? I slightly need to change that. So,
but I have one question. But doesn't gRPC use actually numbers for procedure calls? As far as I know.
I can't really tell you what the protocol does internally, but imagine this only works when you have need to make dead sure that you have the same method defined on the client on the server side and on the client side. And if you don't know what method is available, and we will see some middleware technologies where the client doesn't know what method is available. And then it needs to know how the name of the method is. And one is not the name of the method. And there might be protocols that transform that, but why call it one? You just use a byte-coded mechanism. It's one is something you do in your mind, but of course they just byte-code it if they want to.
Yeah,
okay?
They use it like that. You give it the naming and you assign it a number, and the parser goes through it, and it's something like that. But it uses internally like the numbers to call the different methods because it's.
Yeah, I might look that up and state that, but there are different other technologies that don't use that.
Yeah,
and therefore, exactly, and therefore, it's one possibility. It works, but you can optimize at a different level. The name of the procedure, and typically you think, let's optimize that, is not the problem. In the whole communication process, the name of the procedure is really the last thing you need to take care of, because when you're there's so much other things you can optimize that this is just a tiny part. Nevertheless, it typically depends on what system you're using, and you're not allowed to do that in our exercise, just to make that sure. Okay. Fine. So this brings us to where does this remote procedure call comes from? And this is something that was constructed by Sun when they experiment with their Solaris network operating system, which are not commonly used anymore. But depending on where you are going to work, this might pop out at some point in time again. So this is just stuff from the history books, and but nevertheless, the interesting part was that in order to specify which methods to call, they used this external data representation, and it had a C-like syntax. So in order to specify what was available, you were using a different language again. And of course, this works perfectly, as many things do work, but which are not beautiful. This, of course, made the life again complicated. In order to do something, and when you want to do something and you have to use a different language, you have to learn the language. Things are expressed in a different way, and therefore, another level of complexity is added. Why not solve the problem with the already at hand technology? And therefore, during or inside remote method invocation, typically this using a different language to specify the interfaces and data and stuff like that was exchanged by using the same technology of the middleware platform, which is nicer because you then just use one language to achieve what you want to. So as you already heard multiple times, procedural programming was exchanged by object-oriented programming, and therefore we had to come up with a new naming for remote procedure calls. And what popped up was remote method invocation. because now the client invokes a method of a specific object, and as we don't have the object locally, we have something that looks like the object but isn't really having the functionality. But this so-called proxy object has the capability of transforming the call of the method and the parameters and all the other stuff that is necessary into equivalent byte array, which is then communicated to the skeleton, and then the real object is called, and then the result is returned and back to the client machine again. So again, in principle, when you take look at it from a higher perspective, it's basically the same thing you want to achieve on the object-oriented world. But as the programming paradigm changed, the name of the concept needed to change, and now it's called remote method invocation. And again, this is not restricted to Java. This is just the concept, and Java just took over the name and used it and didn't come up with a new name. So many people think remote method invocation is a Java thingy, which is of course not the case. And something that is also stated, this having something that looks like the real thing but isn't really the real thing, sometimes is called proxy pattern. So it is behaving like a proxy, like a Stellvertreter on the respective side, and looks like the real object, behaves like the real object, but in reality it is not. It's just communicating if it is necessary with the backend to do whatever you want to do with it. Right, this brings us to Java RMI, which we will use in the next exercise. So we will use Java RMI to build the second server element in our 4-server row. When you try to remember the exercise structure of our system. So we had 4 different, or we will, and hopefully we get there in time, 4 different server technologies involved. One is C++ server, one is Java RMI server, one is a SOAP-based server, one is a REST-based server. And so next step is integrating or using a RMI approach from Java, which is called Java RMI. The good thing about Java RMI is everything, the middleware technology, the middleware layer is the programming language itself. So it's Java we will be using, and we can use object serialization, or can use it in the background in order to achieve what we really want to do. So that's basically the idea. Yeah. Again, keep in mind this openness. So if we want the design goal of distributed systems, this openness aspect. So in order to use these aspects, we had to specify an interface definition language. And as we heard, in the old days, the remote procedure calls had their own very specific interface definition language, which had to be learned, which had to be expressed, which had to be compiled by a specific compiler, and. So this was integrating more complexity, and later on people came to think, why not get rid of this complexity and make it even easier by using the same language construct we use to express or to program our systems. And that's basically what is happening nowadays. So nevertheless, we had some kind of interface definition language, which can be rather specific, or we can, of course, have an interface definition language, which is the same as the programming language we use to really build our program. And that's basically what is to say. So the interface definition needs to be clean and sound. It needs to be complete. Of course, we need to specify everything that is available. It needs to be specified neutral. This, of course, depends on the type of middleware technology we are using. Neutral means, okay, if it's specified in Java, then we can restructure it in Java on the other side, but we can typically not restructure it, or at least not that easy, in .NET, for instance. Nevertheless, as we already heard, we will have some middleware technologies, like for instance SOAP, that specify the interface in a way that is independent of the used middleware technology. So they are really neutral. And if we are restricted to a specific technology, then of course neutral is relative. It's not neutral to everyone. It's neutral to the same Java environment we are using on the other side, but not neutral to a different other middleware technology we might want to use. This brings us to our last system we can use, the so-called message-oriented model, which is also something that is quite old. Nevertheless, I already told you it's also surprisingly young or modern, if you want to call it. Young is not really, it's old and modern, something that is typically not not said about something at the same time. The idea is we send messages. We have some sort of client that sends a message to some kind of infrastructure, and the infrastructure takes care that the message is received, calculated, and provided, and stuff like that. So the idea is some kind of asynchronous mechanism, and based on extensive decoupling of transmitter and receiver. So they are not communicating in a synchronous way to establish something. So inside we use terms like messaging, message passing. We queue messages if there are multiple messages available. Queues may work in first in, first out principle, or there is different priorities are involved, stuff like that. Of course, there are different message passing variants. We can have a point-to-point mechanism where we have two distinct specified partners which want to exchange messages, so a request-reply model. A client issues a request and gets a reply from the server. Or we have something like broadcasting, where we have a message that needs to go multiple other elements that are involved. And of course, we can have a request-reply model with different queues involved, or we can have different receivers. So this is publish, subscribe. We have different queues for topics and subscribers. And this is something that is, as I already said, a quite old approach. Can you name me a modern system that is strongly fostering this this message passing idea? So you've all came across at least one system, everyone in this virtual room came across one of these systems lately. Have you an idea which system uses this message approach? There was a word a message, but I didn't really get it. It was just static background noise. So anyone knows a system that strongly fosters messages, a really modern system, and it's used all over the place, globally. Any idea? 80% of people, or not 80% of the human population, but quite a huge chunk of the human population uses a system that strongly fosters message-oriented communication. No idea. Especially mobile computing students should be aware of that.
Talking about WhatsApp or?
not a program.
Please repeat the question.
Could you please repeat the question? So what modern system you, at least mobile computing students, and I think automotive computing students also have experience with that uses strongly message-oriented communication inside?
Android.
Android, exactly. Android, Intense. So if you're doing Android programming, you use a system that is based on message-oriented communication. And typically we tend to think, okay, message-oriented was envisioned 30 years ago, 40 years ago. That's crap. No one will use that anymore. But as I said, of course, we won't use it in the way it was envisioned and implemented 40 years ago. But the concepts are always constant. And if you remember the concepts, you can reuse them throughout your whole working lifetime, which will be quite a lot of years to follow. So keep that in mind. Even something that was envisioned ages ago is still usable and practically usable in technologies today. And you will find that out in a decade or 2 or 3, and then things pop up and you think, well, damn, that's old crap, and they just gave it a new name. But that's the way it is. So as I take a look at the clock, we are already over time, so we just hurry up. Application-oriented middleware is also something that was envisioned at that point in time, making the middleware technology even more powerful, more supportive, not only communication, but also other stuff that it took care of. And if you think about, again, Android and think about frameworks and fancy libraries, where you just need to define components, and these components then run inside an environment that takes care of all the rest, you see it's some kind of application-oriented middleware. If you take a look at it from a middleware perspective, of course, then the others say framework is something completely different, but always depends on your point of view. So application-oriented middleware strongly is aiming at aspects that are supported by some kinds of frameworks. And of course, Android is the prime example at this point in time where we have a framework inversion of control, components, extension points, and all that crap. And this is all part of the ideas of the application-oriented middleware. And if you realize that, then you can reuse your knowledge that you gained in your studies, in your schoolwork, and this can be found everywhere. You just need to be open-minded and take a look at it from a more general perspective. And we all tend to be too specific, too problem-oriented, and it is necessary to open up on that behalf. But this is something that we tend to realize when we are getting older. So runtime environments are involved here, some kind of services that can be used inside the runtime environment. And it's all the same: naming service, session management, transaction management. You all do that, and you get that from fancy libraries and fancy frameworks. And it's all basically old ideas realized in modern software. And therefore, we are talking about that. So this brings us to an end, 5 minutes late. Thank you for your attention. I will be closing the lecture call now and open up the respective exercise calls. Yeah. As I said in the beginning, those of you who have already finished with the exercise, join us for a moment, send your excuses, and then you can leave. The other ones, continue with your exercises, show me your results, and then you are free to also leave early or stay till the end and work on your exercise. Have a nice one. Bye.
Bye-bye.
Bye.
Bye.
Okie dokie, let's close that.